Okay, we continue last video. Kalman filter from last video. I think you already know about the basis Kalman filter and how it works with the state prediction and measurement update, and I tell you some example. Now we and the last example I told you about coding this programming, coding this Kalman filter example. So you can see here we call library right here is easy, and we call it tupple. In the Visual Studio 2016 you can include tupple, it's already there. So 2019 Visual Studio 2019 they include they already have a tupple, and we create the new variable right here. We create two functions right here. Type tuple is vector, right? And we use the formulas in last video for the update measurement. You got the new mean and new covariance, okay? And in the state prediction is a similar way. We got the new mean, new variant for covariance for the state prediction, right? And the return the value for you. You want to figure out how the tuple works? Let's click on the link. I remember I provide the link. How about the, I don't know if you don't have, I will provide the link in this video about the tuple. Okay, so in the main we just call the measurement. We declare the measurement and the uncertainty for measurement. Similar way, the motion and uncertainty for the motion. And remember the Kalman filter cycle, we have the initial state where they start. They start from the initial state. We assume the uncertainty for the first, but for the initial state is the 1000. It's really big because we don't know where the robot is in the first time. But after several measurements, you got the correct you got a good result quickly. So call the for loop right here. This one return the element number of element into the array. So you can write here, you know, 4 about equal less than equal 4 is work too. So but for practice C++, you have to understand what it means. Okay, that's and you print call to function and print the result. Okay, it's easy. See, they print the result look like we talked last time in the last video. The result for the update, prediction, update, prediction, update, prediction. You see, you can change the value inside and you see how the results change and how the covariance of and the impact to the value of the result Kalman filter, right? So okay, we go back to the lesson to the topic to talk about the multivariate Gaussian, right? Last time we talked about the one dimension, and what about two dimension or higher dimension? So how the Gaussian look like is 3D Gaussian, and 2-dimension Gaussian we declare about two variable state variable. For example, right here you have the mu x mu y, okay, for the mean. And for covariance right here, we have the matrix right here for the covariance, S and Y, okay. And here's the how the Gaussian is look like, the coordinate. For example, right here we have the covariance for x and y is equal. It's a cycle Gaussian right here. But if we have different variable and covariance x, y, and correlation, so we have the different shape and of the Gaussian. Okay, so that one. That's introduction a little bit about multi-dimension right here in the Kalman filter. So you see as sigma sy and ys is correlation term. So and right, as the more interesting thing is to the higher dimension is you have the s value for mobile robot. If you have the s value, the position value, and how to derive we can get the velocity value too. S is mean you can the two-state variable, higher two-state variable, okay? And s is right here the position, and we derive the velocity. S it means we can measure from the sensor is the observable value, but the s dot velocity is a hidden value. It's the same way for one dimension. Kalman filter we have initial value and state prediction. Okay, for example, we have the model motion right here. S prime is called as the previous one plus for the displacement after the delta t. Okay, and we have state prediction when we have initial belief and the shape of the Gaussian or something like this. Okay, and they do the same way after, for example, they move 50 meter, so they have a measurement update, and you have the posterior belief after time t. Okay, so we have the model for the motion of the robots right here. It's really easy. The s prime, the distance, time t plus 1 equal time t plus the displacement, okay, after time delta t, okay, and s dot right here is called s dot because we assume this model is constant velocity. So from here you can guess this one easily. If somebody already know about linear algebra, you can change from this model to the matrix model right here as this state space model. So we can get the, you look at it right here, 1 0 delta t 1, right? That's the they call the state transition function. Or if somebody learn about control system, you already know about state space model. So that's the ideal world, so they don't have noise. But in reality, so the equations to maybe change. We had to plus with the noise, right? The noise right here is mean the process noise, not processing. It mean the more. And to calculate the posterior covariance, so we have the S right now here, S prime equal the state transition time S plus noise. And how about the covariance? How we calculate covariance? It's a little bit complex. Right here you have the formula right here, and now we update the mean and covariance as a part of the state prediction. So I have a question to make you more understand about for the higher dimension Kalman filter. So we tracking some object, for example, the pedestrian pedestrian, the autonomous vehicle tracking the pedestrian move x and y z, and they have velocity of vs and vy. So find the state update function f, okay, from time t to time t plus 1. So we have the state transition equation right here as prime for equal f times s. So what the f right here if you already have the 4 dimension right here, okay? So maybe what do you think? The four of them, what do you think? Which one correct? So you will got the answers right here, okay? It's easy. You can create the state model, right? Something like this, okay? And you got transfer to this, okay? You change to this, and you get the state transition function app right here. But right here is quite simple. But right there you have about four equation, okay? And another example, something you tracking position, velocity, acceleration, and quadrature in the vertical dimension z, and the state of quadrature can be represented as so we have the s, z, the height or the velocity, acceleration. So what the function f right here from time t to time t plus 1, we have the same thing right here, and the answer is, which one is correct? Okay, right here why you see this 1/2 delta t square, because when you write the formula, the motion model, you will got the acceleration inside, right? Because s plus s dot delta t, let's add 2 dot square 1/2. You remember the that's motion model in the physics, 1/2, okay? Delta t square. So that's the first phase is the model of the first day about the prediction. How about the measurement update? So measurement update is quite easier because we got the value from sensor, right? And z is present for the measurement update. We change to we got the s dot equals 0, because actually s dot is nothing inside, but we have to write into the metric the state space. So we calculate the measurement. In the measurement update, we had to compare the measurement value and the prediction value. And we got this equation Kalman filter gain. Because the measurement, they had the noise inside, right? The sensor measurement noise or uncertainty of the measurement, so they had to add this value into Kalman gain, right? The first time they see the difference between the measurement value and the the last state prediction value, right? So after that, they add to the noise of the equipment, right? The noise of the measurement. So they calculate the Kalman gain. The Kalman gains mean determine how much the weight you should place on the state prediction and how much on the measurement update. So we got the gain value, and after the gain value, you calculate the update measurement. We got the S and covariance matrix right here. So you remember we have two state. One state prediction and second will be measurement update right here. So generally we have whole in the state space in many state variable you have this formula. For example, you don't need to remember when you need it to open and write down into the code. Okay, the state prediction you have in the state prediction you predict the S and covariance, right? Position and covariance, and the measurement update you find the error, the differences, and you got the common gain, and after that you got the update, the value S and P right here, covariant, and position value right here, state. So that's it. So for the multi-dimension for covariant, you have this formula, right? So how to apply into the code? How you write the C++ with this formula? That's a question. You already know about the first one dimension, so right now we calculate two dimension, higher dimension two. With this formula, it's pretty useful for you. Okay, now you go to the C++. Okay. Right here, you see last time I told you about the eigen vector, right? The eigen library. Right. And how you ask the eigen library is help you to do the linear algebra calculation. You multiply, transpose, or there's a lot of stuff right there. So you can multiply something, you can transpose or inverse something. It's easy to use. Right here we you using to declare something CL. If you don't declare right here, when you type in the code you have to ask the column std column CL as right here. If you do something like this, let's say CL or endl, you can do. So we declare a variable right here. Look like last time I told you about the object state P, U eternal motion, and right here the app state transition matrix and measurement matrix, or this measurement covariant matrix. Okay, process covariant inside in the that time I already told you. Okay, in the main we see you can have the vector at equal the two dimension. Okay, 0 0 right here we got the 2 by 2, the matrix 2 by 2, right? And right here we got the matrix 2 by 2 to the state matrix, right? And we got measurement matrix H right here, and we got the covariant for measurement covariant R noises and the identity matrix and the Q process noises right here. So we say push back in the vector, we push back this, we declare vector S, and we say in the vector, and we say 1, and we push back into the measurement 2, 3. For example, we add all this value into the measurement. Okay, because we declare the measurement vector right here. So right now we use all value into the measurement. Into the filter, so into Kalman filter, so we got the we remember the formula last time I told you. So we have the y as k common gain, okay, and the new state, okay, just the update measurement, and right here we calculate the prediction. The type in the formula right here. And you have the prediction, okay, so let's see. So we see the update and the prediction. Okay, you can see they update the value, the state of the object, position, and velocity, right? As the first time the covariance is really big. So you ask them move 1 and they update the value for 99. Good, right? And that's it. It's pretty easy.